Hi, today we're going to talk about hidden Markov models or HMMs. So HMMs are really popular machine learning algorithms to handle sequential data. So this is the outline. First of all, we're going to talk about what sequential data is, and we'll talk about Markov model, and we will extend this one to hidden Markov models. And then in this section, we'll talk about the architecture and the graph. And then we'll talk about three main problems in HMMs: evaluation problem, decoding problem, and learning problem. So evaluation problem means we have to evaluate the sequence given an HMM. Okay, so when we have an HMM, then given a sequence, how likely this sequence is in this model. Okay, and we will learn the backward or forward or backward algorithm. And the decoding problem is that when we have an observations, then what is the best sequence, best hidden state sequence. We will learn the Viterbi algorithm, and the last one is a learning problem. So, given this a lot of sequences, then we have to train the HMMs. HMM has a lot of parameters, so we have to update all the parameters based on the training samples. And then we'll talk about some other issues. So first, the sequential data. So in pattern recognition or machine learning, we usually assume that the data samples are IID, so identically independently distributed. Okay, so this is kind of the basic assumption. So in this case, the likelihood can be expressed as the product of all data points like this. So we use this product, and when we have n samples, so this is one likelihood for one sample, and then the likelihood of all the data samples can be just product. Okay, but this assumption is not valid for sequential data. So when we have a lot of samples in this sequence, these samples in this sequence, they are not independent. Okay, so think about the temperature. So when we have a temperature sequence, okay. So this one is actually seasonal data. So if the yesterday's temperature is somewhere around here, then today's temperature is not that different from the yesterday's temperature. Okay, there is some strong correlation, something like that. So this IID is not valid anymore. Okay, and then the sequential data includes time series data like stock price, the speech signal, and DNA sequence data and sentence. Sentence is a sequence of words. Okay, and there are a lot of sequential data, including some kind of sensor signals and etc. And we focus on stationary sequential data. Stationary means something like this. So the statistics of the distribution of this distribution are not changing over time. So even the amplitude are changing like this, but when we check the average, then the average is not changing that much, and the variance is not changing that much. But this one is one example of non-stationary process. So when we check the average of these samples and the average of these samples, they are different. Okay, or sometimes we have the same kind of average, but we have different kind of frequency. This is also non-stationary. But anyway, so the stationary data means the statistics of the distribution are not changing over time. Okay, so when we handle sequential data, there are a couple of issues, basic issues. First, the order should be considered. As I said, this is not IID, so we have to look at the data samples with the dependencies, and especially in the sequential data, we have temporal dependencies. Okay, and without the temporal dependencies, we cannot understand the data set. Okay, so it's important. And the next one is length. The length is flexible. Okay, and then the speed is flexible. So when we read one sentence, okay, like I love you, and this input is fixed. So we have only 3 words. But when I read this sentence, sometimes I can read this sentence really quickly, sometimes really slowly. Sometimes I I read this word really slowly, or I can read this word really fast. So there are a lot of different kind of speech signals for this sentence. Okay, so when we have a different length and different speed, then our model should be flexible enough. Okay, so if the input dimension is fixed, then to handle all these different lengths, then there will be a problem. Okay, so the model should be flexible too. And the time resolution of input and output might be different. So for example, in the speech recognition system, we have audio signals every 10 milliseconds, and then we have to recognize the phonemes, and then phonemes should go for like more than 10 milliseconds. Okay, so we have one phoneme over 5 input samples, like a 50 millisecond or something. So this one would be K. Okay, something like that. So input has a different resolution, and then the output has different resolution. Okay, so that is another big problem, big issue. And as another example, if you have a language translation, when we have one sentence input source sentence from the source language, and then we want to translate to the target language, and obviously the length of this sentence would be different from the length of the target sentence. Obviously, sometimes they would be the same accidentally, but most of the time they will be different, slightly different. So what I'm saying is that the input sequence is really flexible, the length is flexible, speed is flexible, and input-output, the relationship between the length of input and output, these could be different, so pretty much is flexible. Okay, so to explain the relationship between input and output, then we have this slide. So sometimes we have one sample as an input, and then we have a lot of output. Think about image captioning. So we have one image, then we have to generate one sentence to describe the image, then we have a lot of words. Okay, and then there is a many-to-one kind of relationship. So text categorization is one good example. So we have a lot of words, and then we have to classify this text. Or we have different types of many-to-many relationships. So this is something like a translation, and this one is something like a speech recognition. Okay, now let's talk about the modeling the sequential data. Okay, so when we have a sequence, then the probability of a sequence can be represented with this product rule. So this is a probability of a sequence. So we have a sequence, okay, n is actually a time. Okay, and then this one can be decomposed into this one. Okay, this is not an approximation, so this is exact the equation. So we have a p of x1, okay, because x1 is the first sample, and then we have a probability, conditional probability, and this one is a probability of xn given the previous history samples. So given all this history, then what is the probability of xn? So we apply this product rule. So in the predicting the future event based on this observation sequence, we are interested in this probability. Okay, so it is not practical to consider all the dependencies to the observations. So if we have a long sequence, then this could be like the length of this previous could be like 100. Then we need to capture all the relationship between xn to x1 and x2 and to xn minus 1. So it's really complicated. Or The other extreme case is that we can treat all the observations independently. Okay, so it means we are gonna ignore all the temporal dependencies, so it would fail to capture the temporal dependency. So we cannot actually handle the data properly. So we have to compromise between these two extreme cases, considering all the history or ignoring all the history. So these two extreme cases, we have to compromise. So Markov chain, the simplest one is the first order Markov chain, and then the next one is second order Markov chain. So in the first order Markov chain, instead of considering all the history, we just consider just the previous one. Okay, so as you can see here, when we model, when we are interested in x3, then we will just check x2. Okay, so x3 has nothing to do with x1 when x2 is available. Okay, so that's the first order Markov chain, and the second order Markov chain means we consider the previous two samples. So when we are interested in x4, then we will check x3 and x2, not x1. So we consider just previous two samples. So it's not just about the temporal dependencies. So when we have an image, okay, so we have a lot of pixels, okay. So if this pixel is related to the neighbors, not the other pixels, then we can say, oh, there is a Markov property here. So when we look at one observation, this observation is related to the neighbors. That is a Markov property. And in the temporal data set, when we consider just the previous sample, then it's a Markov chain. Okay. And we assume that it is homogeneous Markov chain, which means P of xn given xn minus n is always the same. So P of x2 given x1 or P of x3 given x2. So these probabilities have the same kind of equation. So we use the same model to have P of xn given xn minus 1. So it means P is the same over all the time. So if x1 is, for example, the observation is discrete, then x1 is a 1 and x2 is 3. In this case, if x2 is 1 and x3 is 3, then these two probabilities are the same. Okay, so that's a homogeneous Markov chain. Okay, and in this case, when we have k discrete states for observations, then this Markov chain can be modeled as a k by k matrix. Okay, or if we want, we can have parametric models to model this Markov chain. Okay, now we talked about the Markov model, but as we did in the previous chapters, we can think of a latent variable. So in the clustering, when we have observations, we consider the cluster index as a latent variable. Okay, and then in the generative perspective, from this cluster index, we generate all the observations within the cluster. Okay, or in the PCA, we consider the low-dimensional representation would be the latent variable, continuous latent variable. And from this low-dimensional representation, we have observations. So which means the low-dimensional latent variable actually generated these observations in high-dimensional space. Okay, so likewise, in the hidden Markov model, we have a latent variable. Okay, and then this is a hidden Markov model graph. So in this case, the Markov property is on the latent variable. So when we are interested in Zn, then the Zn is connected to Zn minus 1, not to Zn and Z sub n minus 2. And given this latent variable, then we can make an observation xn. So when Z sub n is given, then xn and xn minus 1, they are independent. And we can represent this graphical model with joint probability like this. So as we did in the mix of Gaussian model, when we have observation and we have latent variable, then including this latent variable, then we can have a complete likelihood as a joint probability. And then the Markov properties are on this latent variable. Then we can have the probability of this sequence of the latent variable from z1 to zn. And then given one latent variable gn, then we can have xn. So we have a product. So this is a complete equation for the hidden Markov model. So from z1, so we have to have a probability for z1, and then given z1, we can generate x1 by this. And then from z1, we can generate x2 by this. So repeatedly, we can generate all the latent variables and then the observations. Okay, and basically there are two different models by the graph depending on the latent variables. So when the latent variables are discrete, if zn, these are discrete, then it is hidden Markov model. So with hidden Markov model, we can have a discrete observation or continuous observation, but the latent variable should be discrete. Okay, and then if the latent variables are continuous, then it is a linear dynamical system like a Kalman filter. So in this chapter, we're going to talk about hidden Markov model, which means all the hidden latent variables are discrete. Okay, and then we'll talk about discrete observation and continuous observations later. Okay, in HMMs, we have two different probabilities. As you can see here, this one is a transition probability basically, and this one is emission probability. Okay, so transition probability is about the transition between the hidden states from n-1 to n. And as I said, it's homogeneous. So we don't have to have a different probability for a different time step. Okay, so we don't have to have a Pn of Zn given Gn-1 and Pn-1 Gn-1 Gn-2. We don't have to have a different probability for a different time step. It's homogeneous, so we don't need this subscript. So we are interested in just the P of G sub n given G sub n-1. And since these are the discrete, so this can be represented as a matrix A. And then obviously it should be a probability. So this sum should be 1. And the first hidden state, P of Z1, is pi. So this one is different. As you can see here, P of Z1 is different from other transitions. So we need this as one parameter, and then the A is a transition matrix. So we need two parameters here. And we can have a transition diagram like this when we have three states. Then from the state 1, we can move to the state 2 or state 3, or we can stay there. Or we can unfold this graph so that we have n-2, n-1, and n+1. Every time step, we have three possible states, and we choose one step. For example, at n-2, if we are at the state 2, and from here we can move to the first state or second state or third state. Okay, and then if we are at the third state at time n-1, then we can move to the first, second, and third. So every time step, we have to choose the next state based on this transition probability. And for your information, in the speech recognition systems, when we use HMM, we have like a 4,000 or 6,000 hidden states. Okay, it's not just a simple 2 or 3 hidden states for a big application problem. Okay, and then we have emission probability. Okay, so emission probability means this one, from Zn to Xn. Okay, so we have emission probability parameter, phi. Sometimes we put this parameter in the equation, sometimes we don't. Okay, but whenever we have this p, okay, then even without the parameter, there is a parameter. If the equation is not confusing, then we don't put the parameter in there. because it's obvious sometimes. So sometimes we don't have the parameters, sometimes we have parameters. Okay, so this is exactly the same as P of xn given zn. Okay, and this probably could be any distribution, but usually we can have a discrete tables when the observation is discrete. Okay, so from this discrete variable to the discrete observations, we can have discrete tables to have all the probabilities. Or if xn is continuous, then we can have Gaussian. And if xn is a little more complicated continuous variable, then we can have a mix of Gaussian. Okay, and then sometimes, even though this is what we need, but sometimes we can have this one, P of z given x. So this one is actually a kind of classification model. And from this model, we can actually estimate this one with the Bayes rule. Okay, not exactly, because there is other kind of constant terms, but roughly we can estimate this one from this classification model. And as in transition probability, it is homogeneous too. So this one, so from state 1, we can have this probability, and state 2, we can have like this. Okay, but it is the same always over the time. So P of xn given zn is the same as P of xn minus 1 given zn minus 1. Okay, so we have the same parameters for the different time steps. Before talking about the three main problems in the HMMs, I want to summarize HMM architecture as a generative perspective. First, with transition and emission probabilities, and the likelihood of HMM can be defined by this. P of observation and the latent variable given all the parameters could be like this. The first state, and from n-1 to n state, transition probability and the emission probability. Okay, so when we generate one sequence with HMM, we can follow this recipe. So first, we can select one hidden state, z sub 1, using pi. So pi is the probability of the first hidden state. And then we repeat this n-1 times. Okay, so now we have a z sub 1, and from g sub 1, we generate x sub 1. Okay, and then we move to the next state. So now z sub n plus 1 is a z sub 2. Okay, so now we have z sub 2, and then repeat, and then from g sub 2 we generate x sub 2, and then we move to the next state, and then we generate in the next state. We'll repeat n-1 times. So by doing this, we can generate observation from x1 to xn. Okay, so here's an example. So when we have a 3 states, okay, so first, by this, we can select one state. For example, let's say we are at the state 3. So now we are here. Okay, from this state, we have to generate one sample. So since this state, the emission probability is a Gaussian, it looks like a Gaussian distribution. So let's say we have a Gaussian distribution for each emission probability. Then from this Gaussian distribution, we have to generate one sample. So let's say this is one sample. Okay, and then we have to transit to the next time step, and based on the transition probability, probably in this case, let's say we don't change the state, and then which means in time 2 we are still at the state 3, and then from this Gaussian distribution we have to generate one more sample. Let's say we generated this one. So from here to here, and then apply the transition probability, and then again we are still in the same state, case 3, and then we generate one more sample. Okay, now when we transit, then accidentally we transit to the state 1. Okay, now we go to the state 1, and then from this state 1, then we generate one sample, then that is something like this. So we repeat this n times, then we can generate all the samples like this.